of snow the winter that we monitored. And the minimum subgrade temperature is this purple line. And you can see that over the winter, the minimum temperature that we got to, and this is actually only a month, but I promise it's all 3 months of the winter, was 0.7 degrees C. So we never did actually get to freezing. And that's something that's been shown in Chicago and in Canada as well, that you don't really get frost heave under these systems. Temperature, for summertime, we're worried again about trout streams. And you can see the max surface temperature of the pavement was 61 degrees C, which is really hot, 130, 120, whatever Fahrenheit, really hot. The subsoil interface is this purple line. You can see it's still above the 21 degrees C trout threshold, but we're a lot closer, right? 25, 26 degrees C. So we're doing a lot of good compared to the surface temperature of the asphalt itself. Okay, quick thing about hydrologic soil group D soils. I'm doing a lot of research right now through a national grant, a NOAA grant in Northeast Ohio. So we've got a couple of sites over in Cleveland and then a couple sites in Sandusky. And I'm going to talk to you about Perkins Township real quickly. All of them are retrofit sites. We're monitoring 7 different permeable pavement lots up there from North Carolina, which means I travel a lot, unfortunately. But we have here, you can see these are Marriott siphons that we've set up to do single ring infiltrometer tests, 12-inch diameter, single ring infiltrometer, to try to figure out the infiltration rate of the underlying soil. So you can see we've dug out where we're going to put our permeable pavement. Typically you would do this pre-construction, but here we had pavement that we had to remove, so we had to do this during construction, unfortunately. So the soil is really horrible. It's a D soil. Silty clay loam. I don't even know how there's any loam in it, but silty clay loam is what it's mapped at. We did 2 single ring infiltrometer tests. There are your test results. How fast is that? Very slow, right? 0.01 inch per hour, pretty much the lowest you're going to be able to measure with a single ring infiltrometer. Okay, what I want to show you, we have 3 sites we're monitoring. We have a western permeable pavement application, an eastern application, and then a monitoring well within the aggregate in the western permeable pavement application as well. So here is the western cell. It basically has a standard concrete drive lane, and then permeable concrete parking stalls. This is crowned in the middle such that the water flows to the permeable concrete. Also, the entire rooftop here drains to this permeable concrete, so we have a very, very high loading ratio, 6.25 to 1, I believe, loading ratio. So that's what that means. And then the east cell, and I should mention this has a 6-inch IWS zone. This west cell does. The east cell, again, pervious concrete in parking stalls, regular concrete in the drive lanes. Same aggregate depth, 18 inches, but no IWS. So we're directly comparing no IWS versus IWS in really poor soils. Here we go. East cell, the one I just showed you right here, this bigger one, has a lower hydraulic loading ratio, 1.95. The west cell, 6.25 hydraulic loading ratio. So there's a lot of water coming to that west application. And except for the 2 largest storms that we've monitored thus far, there's only about 15 storms that we've monitored. Except for the 2 largest storms, that west permeable pavement cell actually has less outflow than the east cell. The reason for that is that internal water storage zone that's able to capture a piece of the runoff that is coming in off of the watershed. 5 storms at the west application out of 15 have had 0 outflow, while all of the storms at the east application have had outflow. So again, that's that IWS forcing ponding within the rock, within the aggregate layer, really improving your performance, even over a D soil. So here's the water level. We have basically a well, perforated well, so that we can monitor water level in the aggregate as a function of time in that west cell that has the IWS zone. And here's an example of the water level measurements. This is temperature, so don't worry about this. This is not rainfall, but this is the water level. So these are rainfall events. Right here, and right here are rainfall events, right? Where you get spikes in level in the well. So what we did is we looked at the drawdown rate in the inter-event periods. So when it's not raining, as you can see, those are marked here between each of the storm events. We looked at the drawdown rates. And as I mentioned earlier, we had 2 pre-construction tests that were 0.01 inches per hour. And here are our measured drawdown rates thus far for the inter-event periods. You'll note they're all very, very low and all pretty close to that 0.01 inch per hour infiltration rate. So 0.016 is actually the average if you average all 12 of these. And so I think that single ring test, very simple, 12-inch diameter, pounded into the ground, Marriott siphon to get a constant head of water on the underlying soil, will give you actually a fairly good estimate of that underlying soil infiltration rate. And that is a heck of a lot easier if you've ever done infiltration testing than doing a double ring test. Just a lot less water, a lot less to carry around. So I think this is the way that we may start recommending things in North Carolina. This is still preliminary though, obviously. So if you look over the first 3 months of monitoring, we had that west application is 2,600 square feet in surface area. And again, we have that 6-inch upturn, so you have to fill that aggregate layer with water. And so here's the change in stage during, basically the change in water level during the inter-event period. And you can see the maximum drawdown is only 1/4 of a foot, or 3 inches. So there's always water in that internal water storage zone because it's 6 inches deep. But what that does is it puts water into the ground. So in this case, we put 1,328 cubic feet of water into the ground in the first 2 months of monitoring, which equates to about 12.5% of the water coming in off the watershed. Which sounds like a small amount, but remember, we've got basically the worst soils you can have, and we've got a 6.25 to 1 loading ratio. So pretty bad conditions, and we're still putting 12.5% of the water into the ground. So it really speaks to what the internal water storage zone can do. One comment, if you have shrink swell clays, you probably do not want to use an internal water storage zone for structural purposes, unless you line the system with an impermeable membrane, because if you get shrink swell that's occurring, you're obviously going to get structural issues with the pavement. All right, on a slope, can it work? Yes, it can. This again is Elizabeth Fassman's work. Here's one of her hydrographs. I showed you some of her data earlier. This is inflow here, and then outflows in green. You can see how much mitigation there is. This is on a slope. However, what you have to do is you have to create reservoirs, if you will, underlying your pavement. Otherwise, all that water will go to the far end, and you'll only have a very little sliver that's being used for infiltration, right? So what we do is we create basically baffles underlying the pavement. Our first effort at it was concrete, which, as you can imagine, was very expensive, one. And two, because the concrete is really rigid and structural, and the aggregate does settle roughly 1/4 of an inch after construction, we had differential settling in the parking lot because there was no settling over the concrete and there was settling right here. And so that causes tripping hazards, and so we're not recommending concrete anymore. We're using either aggregate or just earth overlain with an impermeable plastic liner like a pond membrane, or pond liner if you will, to create berms between each one of these sort of aquifers, if you will. Does that make sense to everybody? Yeah. Okay, water quality, quick things on water quality. So we compared a lot of times the runoff to the water coming out the underdrain. That should say drainage, not exfiltrate, but drainage. Phosphorus, pretty good reduction in phosphorus. It's typically sediment bound, so you can see inlet versus outlet in yellow. Across the board, pretty good performance. Metals, you're going to get very good performance again because you have filtering of the sediment at the surface of the pavement, which is what causes clogging. TSS, again, this is TSS from permeable pavement compared to TSS from impermeable pavements across the world. You can see generally 10-fold less TSS leaving permeable pavements as opposed to roadways, which makes sense. Total nitrogen. This is a really busy graph, but this is again the Kinston study where we had the 4 pervious pavements side by side and then asphalt. And you can see they're all pretty much the same. There's not really any one pavement that performs any better than the others, and they're all around 1 to 2 milligrams per liter nitrogen, which if you know anything about urban runoff is not that good. So you don't get that much treatment for nitrogen. There's just not a carbon source for denitrification. There's not really suitable living environment for microorganisms in aggregate, which is what's underlying permeable pavement. So nitrogen improvement, maybe not so much. I really hope that's photoshopped. Because, yeah, it's got to be photoshopped. Anyway, permeable pavement is really similar to, in terms of performance to sand filters. You get very good particulate-bound pollutant removal, and any of the dissolved stuff, nitrate, orthophosphate, you're not going to get much improvement on at all. So I've just said all this. Metals, thermal pollution, we've looked at temperature substantially. You do get thermal pollution mitigation. pH, you do get buffering of that. TN, not really, and TP, yes. Okay, I'm going to quickly go through an installation case study. I'm actually going to take you through the Boone site quickly. I want to make this comment. You really want to get a contractor that's done this before. You don't want to be the first person that they work with because it's going to make your life miserable. There are lists of people out there that in our case, Carolina Ready Mix Concrete Association, but I'm sure Georgia has one as well, that can provide lists of people that have been certified. ICPI certifies people for interlocking concrete pavements. So you really want to have someone who knows what they're doing put these things in. So 5 steps, typically: soil excavation, bringing in the gravel base, pavement installation, and then you're done. So soil excavation, I just want to make the comment, you want to keep heavy equipment off as much as possible. So if you have a small application, if you can dig from the outside and not get your excavation equipment on the pavement, that's the best thing to do, or on the underlying soils, that's the best thing to do. Installation of PICP and concrete grid pavers, I'm going to take you all through this real quick. So here's our cross section, I showed this to you earlier. Concrete grid pavers, this is my one slide for those because we don't really recommend them anymore, but you can see it's a 57 stone, washed 57 stone base. That word is important. I want to make sure you guys see that. You don't want to have a lot of dust on this stone. It's sand typically, and then the grid pavers obviously are placed on top of a flat washed 57 stone base. Gravel base, what you'll typically see, that's my hand, so normal size hand. 78 stone is the small stone that's used as a bedding course typically. You'll also hear 8 or 89 stone thrown around. Any of that is just fine. Just depends on which quarry you're working with as to what they call it. 57 stone, pretty much every quarry is going to have 57 stone. It's a very common, nominally 1-inch diameter stone. And then number 2 stone, or number 3 stone, or number 4 stone, any of that is fine. It's typically railroad ballast size, so you can see it here, 4-inch nominal diameter. You get a lot of porosity. That's what's used as your sub-base in the bottom of your cross-section to provide porosity to store the water. You do need to compact the aggregate and the pavers, concrete and asphalt as well. They recommend compacting the aggregate underlying so that you get good structural support for whatever paving layer you're putting on top. They say a 10-ton roller, which is what they have here. I've also done 3 passes with a standard plate compactor, and that seems to work fine as well. Edging, you do need edging for both PICP and concrete grid pavers. You're typically going to do this after you've added your stone reservoir. They're typically standard concrete curb and gutter. I like to, again, bend the gutter pan out away from the curb instead of toward the curb to push the water onto the pavement as much as possible. So this is what the edging should look like when you're done with PICP. It should be nice and flush with the PICP. If you don't do this, this is what you get. You get failure at that point typically because your asphalt is a flexible pavement. This will flex some and this will cause failure along that point. So you do need concrete edging to lock those pavements into place. All right, so Boone, welcome to Boone. As I said, we got 96 inches of snow the year we monitored, and snowfall has been seen every month except for July in Boone, which is pretty hard to believe because we're still in the southeast. So construction took 6 weeks, mainly because we had a bunch of monitoring equipment that was going in. It would have taken 2 weeks otherwise. You can see it's 8 parking stalls with a center drive lane. This is King Street in downtown Boone. So here's the lot. This is before construction. It was a gravel parking lot in the existing case. We excavated down about 2 feet across the entire site. Of course, you find all kinds of good things. This was an old gas station, so we had to do monitoring, groundwater monitoring for a year before we were allowed to do this to make sure there wasn't contaminated groundwater plumes. We ripped the subsoil, as I mentioned earlier. You can see our separator walls, concrete separator walls that have gone in here. So those were expensive, and they also caused differential settling, as I mentioned, of the pavement surface. Question?
Is one better than the other for a parking lot versus you use the pavers or use the concrete?
It's, in terms of performance, no. It's basically what you like aesthetically. The PICP tends to be the most costly, and then concrete and asphalt will be similar in cost if you use the expensive binders for asphalt that I think you need here in Georgia given your heat during the summertime. Question? I'm going to talk ad nauseum about maintenance.
What is your best material now for creating these barriers?
We use soil draped in a 30 mil plastic liner. And we compact the soil before we put the liner over it because you do want that barrier to be solid. Yeah. So we'll create like a flat top on the barrier and then 3 to 1 side slopes typically to break up each. In this case, this was just for monitoring. This is a flat parking lot. But if you have a sloped site, we'll use soil.
Test your compaction on the barrier.
You want to, yeah. Yeah. As much as you can get is what I would say, yeah. 95. Proctor.
What about that corrugated metal strips that you use like lining and flower bed?
Mm-hmm. You want to use that?
That's plausible.
Yeah, it could be. You just want to make sure the water's not going to move through it. Yeah. So whatever you can find that's impervious that's going to last is what I would say would be fine. Yep. So these are our under drains. You can see the under drains in each of the cells here. The 3 cells that we're going in, we had a standard under drain in cell A, the 12-inch upturn in cell B, and then the 6-inch upturn, which you can see here in cell C. Under drains have socks on them. We don't really recommend those anymore either. This was 4 or 5 years ago when we built this. Okay, washed gravel. Is this washed? No. So I was cracking knuckles and cursing as this came off. I tend to curse a lot, and I was definitely cursing when this came off the truck. And so, you know, this is really a critical point to have somebody on site, whether it's an engineer or somebody that's doing construction oversight. You want to make sure this is washed. Why would you want it to be washed? Because if it's not washed, Mother Nature is going to do it for you during the first storm event. And you're going to get all these fines clogging the underlying soil, and it's going to decrease your infiltration rate substantially into the underlying soil. So,
you will also consolidate that. You have washed them and consolidate the water.
yeah. Yeah, the other thing you want to make sure you have is washed and angular stone. You don't want river rock, you want angular stone because that locks together. You want stuff that locks together, has as much